Okay, welcome back for Unit 4, Exponential Functions. A lot of this chapter was review, and there was lots and lots of little bits of things that we did. Um, some new, some review, exponent laws, graphs of exponential functions, which we're not, I don't think we've got an example of that in here, but you're responsible for being able to draw the graph of an exponential function without technology using nice points, solving exponential equations numerically and algebraically. Numerically would be just guess and check. Algebraically, we'll see an example of that here. The big new thing that's important for this course, and it almost makes this whole course important, is well, of course it's an important course, but this logarithms is an important topic for where you're headed in college, and we'll practice that a little bit. And then solving exponential function problems. So some examples, some log rules here, evaluate this, and the whole idea is if we can do this without a calculator, that means I've got to be able to write this as 3 to the exponent something, because whatever that something is, log base 3, 3 to the exponent whatever, if I can do it, then this sort of cancels out, and I'm left with just the answer, which is square. So the question is 1 over 243 is 3 to the exponent what? Well, since it's 1 over, I know it's negative something, right? So I got to figure out on my calculator, 3 to the exponent what is 243, and you can mess around with your calculator a little bit. It ends up being 5. And so this is 3 to the exponent minus 5. Again, it's a minus because it's 1 over, and so the entire answer is just plain old minus 5. On this one, 125 over 64 to the exponent negative 1/3. The fractional exponents means root, negative exponent means flip. So how we handle this is we flip it first, and that we don't flip the exponent, just the base, and the exponent 1/3 means roots, so it means the cube root of 64 over 125, which is just the same. And of course, some of these steps you can skip, but it means this, and that means just good old 4 over 5. Yeah. There's some of these that if it was, let's just keep going. What's the next one? Aha! This is the idea of solving an exponential equation algebraically. One of the techniques we had is to put this into a graphing calculator, right? Graph the left-hand side, the right-hand side, and use the intersect function. The idea here is if we can do it algebraically, in this case we can, we have to get full credit, okay? And so the idea is we want both sides to be the same exponent. Notice that 4 to the exponent, whatever that is, 3. I can't write 8 as a power of 4, so what I'm going to do is I'm going to write them both as 2 to the exponent something. Well, 4 is 2 squared. That base 4 becomes 2 squared. The base 8 becomes 2 cubed. And the exponent is x minus 3. And then I can simplify the exponents. Exponents on exponents and multiply. Multiply the exponents like that's in brackets. And as soon as I have 2 powers, the same base, the bases are equal, the exponents are equal. So I can say 6x equals 3x minus 9. That becomes like a grade 9 type of equation. Subtract 3x from both sides, and I get the answer x equals minus 3. On this one, 332 just isn't a power of 7, so I'm stuck. One of the things we could do is on the graphing calculator, put this in, and then look for the intersection, right? Look for the intersection of these two on the TI-83. But we can do better than that. In fact, we learned a way to do this using logs. We take the log of both sides, and the reason why we do that is because the unknowns in the exponent, when we take the log of both sides, the exponent comes down in front. And that was just one of the rules of logs we learned. Then log base 10 is a button on our calculator, and so log 332 over log 7, put that into your calculator in one step, and you should get around 2.98, which makes sense because 7 squared is 49, 7 cubed is 343, so 7 to the exponent 2.98 makes sense. Is there another one on this page? Nope. Let's keep going. Aha. A word problem. Suppose that the current population of a city is blah and decreasing, that's an important word, decreasing at a rate of 0.9% a year. The decreasing means it's exponential decay. And that makes you think of the graph going downhill like this, right? And it also means that you might think of this half-life business, but there is nothing about half-life in here. So I'm just going to use the basic exponential model, and C is the initial amount or whatever. And since it's decreasing, then this is the percent change per year, and it's going down. So this is going to be a fraction or a decimal, right? This is the initial amount. And then I can write a model. Be careful with your decimals here. In this case, R is 0.9%, but as a decimal that I put in, remember, move the decimal place 2 spots, the base is actually going to be 0.991 here. And then there's my model, and if I wanted to use the TI-83 to solve these, I'd put this in as a model, but this is A. Well, actually, I'm not in A yet. What will the population of the city be in 5 years? That's when T is 5, and I can just put that into a calculator in one step. Remember, the city's is shrinking, right? It's decreasing, so this should be smaller than 139,000, but it's not going to be much smaller. And I got, after I clunked that into a calculator, 132,857. And a sentence, of course. Don't lose any communication marks. Please don't do that. You know, write your own sentence. How long before the city population is below 100,000? So in this case, that's the output. You know, how long until the output is 100,000? Well, this is very similar to the question that we solved on the last slide using logs. You know, I can't take the log yet to get the t out of the exponent because this 139,000 is in the way. Divide both sides by 139,000. And I get, on the left-hand side, a nasty decimal that I'm rounding. .991 to the exponent t. And then I've got to take the log of both sides, right? Because I've got to get the unknown out of the exponent. You can almost guarantee that there's going to be some question like this on the exam where you have to solve a problem using logs. T comes down in front. Left-hand side stays the same for now. Divide by this thing. So then I get myself a little more room here. This should be a considerable number of years, right? It's only decreasing by a little less than 1% a year, and you get about 36.4. Notice that you could have guessed and checked on your calculator. You could have used the TI-83 to do this. This is kind of the most efficient, most accurate way that we know. And of course, a sentence there to finish it off. All right, next video is on polynomial functions and equations.